I welcome all of you to the class. As far as the today's class is concerned, in today's class we will be doing the derivation of Clapeyron's three-moment equation. So, as far as the today's lecture is concerned, it's about derivation of. It will be deriving Clapeyron's three-moment equation. So, today's topic is about derivation of Clapeyron's three-moment equation. Okay. So before we understand how we can derive this Clapeyron's three-moment equation, how is it derived? Prior to that, recapitulating the basics is very important for us. So in the previous class, we were talking about the moment area theorem. And we certainly talked about the two moment area theorems, the first moment area theorem and the second moment area theorem. I would like to recapitulate all of you. I would like to take all of you through the short tour of what we have done. We'll recapitulate what we have done in the previous class. And then onwards, we can consolidate on the derivation of the Clapeyron's three-moment equation. When we were deriving the Clapeyron's, when we were deriving the second moment area theorem, while deriving the second moment area theorem, we obtained the expression integral dt is equal integral of x1 m dx divided by ei. And this dt that we were integrating from a to b, as this was the segment of our beam a to b, this integral dt is what we said, this is t subscript b by a, b of a. So we said this is tangential deflection or tangential deviation. We said this is tangential deviation. Okay, this is tangential deviation of what? This is tangential deviation of b with respect to a. Now, this is something that we have to keep in mind, that we are saying that tb by a, that is this distance, is the tangential deviation of b. Okay, and this is with respect to a. Fine. So where is this tb by a first of all calculated? This is calculated at point b. From point b, we are drawing the normal. Okay, we are drawing a vertical line from point b, and that vertical line from point b intersects the tangent drawn at point a at b1. So the vertical line drawn from b intersects the tangent drawn at point a. The intersection is at b1, and we say that tb by a is this vertical distance. Fine. And we say that this tangential deviation of b with respect to a is equal to x1 m dx by ea. Okay, so we have this is equal integral x1 m by ei d of x. Fine. Now look into this expression. We said this entire integral gives us the first moment of, this is the first moment of m by ei diagram. This is the first moment of m by ei diagram. And this first moment we are calculating, we are taking first moment and we are taking this x1. Okay, x1 is the distance from the point where you are actually drawing the vertical line, where you are drawing the tangential deviation. The point where you are calculating the tangential deviation is the point, or is the axis, is the line about which this first moment of m by ei diagram is calculated. This is very, very important point for us. That is, when we are calculating the tangential deviation when we are calculating the first moment of M by EI diagram. Okay, this first moment of M by EI diagram is calculated by taking the product with x1. Fine. And this x1 is the distance of the area from the axis about which from which you are calculating, we are calculating this tangential deviation. So it means this tangential deviation is equal to the first area of M by EI diagram about which axis? About the same axis. Okay, so this is very important. With this concept in mind, what we will do, we will go for the derivation of their Clayperons three-moment equation. So the agenda is the derivation of Clayperons three-moment equation. So we write derivation of Clayperons three-moment equation. So we have to derive this Clayperons three-moment equation. How we will do? Let's take a continuous beam. We'll go step by step. Let's take a continuous beam. This is a continuous beam and these are the supports. Let me take a continuous beam having three supports only. Okay, then we can generalize it for a beam having more than three supports. Okay, and let's suppose that this length is given to us as L1 and this length is given to us as L2. With this beam being subjected to load, okay, let me call this as, this is end A, okay, this is B, and this is C. Okay, this length I will take as L1, this length I will take as L2. Okay, and this beam is subjected to a sort of load. Okay, the type of load on this, it may be a type of uniformly or a non-uniformly distributed load. Let me take a distributed load. We don't know what type of load this is. This is a sort of load acting on this beam. Okay, maybe sometimes this may be a concentrated load, sometimes this may be a uniformly distributed load, sometimes this may be a non-uniformly distributed load. It can be anything. Okay, but every time it will be touching this beam axis, so this is to be corrected. Okay, so this is somewhat like this is the load acting on the beam. Fine. Now, under the influence of this load, okay, this beam will generate, there will be bending moment inside the beam, actual bending moment. I'll say there will be bending moment in the beam. We know that bending moments are created, shear forces are created in the beam, and these shear forces and these bending moments, okay, are created in the beam in response to the external deforming force. So some bending moment will be created. What will be the shape of that bending moment diagram? We don't know what is the shape of the bending moment diagram at all. Let's suppose the bending moment diagram is like this. Let's draw a bending moment diagram as well. Let's suppose its bending moment diagram is like this. Okay, let's draw its bending moment diagram and assume that this is the bending moment diagram. This is the variation of the bending moment. This is how the bending moment varies in this beam. Okay. Okay, this is how the bending moment varies. And this is the second plan. Okay, let's suppose this is the bending moment diagram of this beam, such that this area we call as A1, and let's call this area as A2. This bending moment diagram that we are drawing here We don't know whether this is correct or not. This is called a free bending moment diagram. This is the free bending moment diagram. This is the free bending moment diagram. Let's suppose that the centroid of this bending moment diagram is somewhere here. From here, let's suppose it's at a distance of x1 bar. Okay, and let's suppose the centroid of this area is somewhere here, and from here the centroid here is at a distance of x2 bar. These are the two centroids. Okay, now what we will be doing, these bending moment diagrams, okay, this free bending moment areas, what we are doing, we are treating that this beam is simply supported, because here you are treating the bending moment value to be equal to 0. Here you are treating the bending moment value to be equal to 0. Here we are treating the bending moment value to be equal to 0. That is only possible when the beam is simply supported. But we don't know whether the beam is simply supported or not. The beam may be simply supported, or the beam may not be simply supported. Okay, so when we are drawing this free bending moment diagram, we are assuming that the beam is having two spans. This is span 1, this is span 2. Span 1 is having length L1 and span 2 is having length L2. Fine. And two spans are lying on the simply supports. You have a simply support at A, you have a simple support at B, maybe a roller and a pin support, and you have a simple support at C. These assumptions we are putting in. But that's not always the case. Sometimes we may be having a simply support, we may not be having a simply support. Okay, so it is possible that the bending moment A is not equal to 0. The bending moment at B is not equal to 0. The bending moment at C is not equal to 0, but they may be having some value. Okay, that's what we do. If we say the value of the bending moment at A is MA, the value of the bending moment at A is MA, the value of bending moment at B is MB, and the value of bending moment at C is MC. Okay, then we draw one more diagram. Okay, let's draw one more diagram. We draw one more diagram like this. Let's suppose the value of the bending moment here is equal to MA. Here, the value of bending moment is, say, for example, equal to MB. And here, let's suppose the value of the bending moment here is equal to some MC. Okay, and join these points. This is the diagram of bending moment, not exactly the actual bending moment. This is the bending moment diagram that we are obtaining when we are assuming the value of the bending moment here is MA. The value of the bending moment here is MA. The value of the bending moment here is equal to MB. The value of the bending moment here is equal to MC. Okay. Now, let's draw some more lines. Let's divide this into small rectangles. Let's draw a line from here to here. And also draw a line from here to here. We'll also draw some lines. Let's draw a line from here to here. And we also draw a line from here to here. Okay. Now, if you look at this right angled triangle, let me clean this one. If you look at this right angled triangle, okay, this is a right angled triangle. It will have its centroid. Its centroid will be somewhere here. Its centroid will be somewhere here. Centroid of right angled triangle is somewhere here, such that we know this span is L1, this span is L2, such that From the 90-degree side, the distance of the centroid is at a distance of L by 3, that is L1 by 3. Fine, it's at a distance of L1 by 3. And if you look at this right angle triangle that I just removed, that I will be drawing with a yellow color, this yellow color right angle triangle, its centroid will be somewhere over here. Its centroid will be somewhere over here. Okay, there's a right angle triangle having yellow as one of the side, such that from here to here, from here to that centroid to here, from here to here, the distance will be L1 by 3. Therefore, this distance will be 2 times L1 by 3. This will be the centroid of the second right angle triangle. Okay. Now, what we will do, under the influence of this load, what will happen? The beam will deflect. We don't know how the beam will deflect. Let's suppose the deflection curve is somewhat like this. Let's draw an arbitrarily drawn deflection curve. Let's arbitrarily draw a deflection curve. I will fix this point over here. Okay. So let's say the deflection curve is drawn and it is somewhat like this. It is somewhat like this. This is how, let's suppose this is how the deflection curve looks. Let's say this is the deflection curve. Now the question is why we are showing curve concave here and convex here. The reason is you are essentially having a support over here. So what will happen? This load will move. If this load is moved, then what will happen? This will deflect like this downwards, but this will deflect in the upward direction. If this load is moved, then this will deflect in the downward side and this will deflect in the upward side. Okay, that's quite evident. As long as both the loads, as long as the load is not uniformly distributed, then you will have the deflections on the lower side only. Okay. Apart from this, let's draw tangent to the curve at this very point. Okay, so the tangent, let me try it with some color, is like this. Let me reduce it backwards, somewhat like this. Okay, let me join these distances. Let me join the first one with some black color. This one. And this one I will also join with black color. And then we'll take some other color. From here, we'll take it to the yellow. Okay. We produce this backwards. The intersection is over here. Okay. Now let's say that this angle is equal angle theta. Let's say that this angle is equal angle theta. Okay. And this deflection, this here, this is deflection at end A. Let's call this as delta A. Okay. And this distance from here to here, let's call this as ZA. Okay. Small a, we'll write it. Let's call this a small a. Similarly, let's say this is this much distance. Let's call this as delta C, and this distance from here to here, let's call this as ZC. Fine. In fact, this angle is angle theta. Fine. Now we can clearly say this distance is L1, this distance is L2. Fine. Now what we can say, this is theta here, this is theta here. So in this right angle triangle, tan theta will be perpendicular by base. Okay. In this right angle triangle, the tan theta is perpendicular by base. So you have tan theta here, it will be same. So we can write from both the triangles. Let me write it at the top. The value of tan will be equal tan of theta is equal, it will be delta A plus ZA divided by L1 is equal delta C plus ZC divided by L2. Okay. Okay. So we can write we can still modify it. We can write delta A by L1 plus ZA by L1 is equal delta C by L2 plus ZC by L2. Okay. Now look at this Z. Delta is deflection for us. Okay. This Z and this Z, ZA and ZC. What is this ZA? This ZA over here and this ZC over here. What is it? So what we are doing, you are drawing a tangent to the curve at this very point such that that tangent is intersecting with the normal drawn at another point of the deflection curve. Okay. And you are taking this ZA as one of the distance. And here you are having the tangent drawn to the deflection curve at one point is intersecting with a vertical line drawn at another point. Fine. So if you look at this ZC, this is nothing. This is tangential. This is tangential. This is tangential deviation. This is tangential deviation of C with respect to the central point. Let me call the central point as this is B. Okay, this is B. And if you look at this ZA, this is tangential deviation of A with respect to the central point B. This is what this is. Tangential deviation of A with respect B. This is what we have been doing when we were deriving the second moment area theorem. And therefore we can say, as far as this Z's are concerned, we know this Z from the second moment area theorem. Z is equal M by area under the M by EI diagram. Okay, area under the M by EI diagram, that is M by EI. Okay, and dx. M by dx, instead of dx, we can directly write x. Okay, we can directly write here x. Okay, M is the moment, A is the distance. Okay, so we can further modify this equation as, we can write this equation as, okay, so this is, let me this was integral of integral x1. This is what we had done, mdx. Okay, this is what we are trying to calculate. So this can also be written as, this is integral mx1, or I, instead of x, I can x1 I can also write as x. Okay, so it is mx by ei or mdx. Let me rewrite this expression. This expression can be rewritten as, this is x. Okay, so this is integral m dx by ei into x. Okay, so that is also written as, from the basic mechanics, we write this as, this is equal to area under the diagram, m by a, m diagram, area under the graph, into x bar. X bar is the coordinate of the centroid, divided by ei. Okay, this is a very important equation for us. We know it from the basic mechanics. Okay, we know it from basic mechanics that this expression is, this expression holds. Okay, so what we will do, as far as ZA is concerned, we can therefore write using this expression in this equation. Let me call this as equation 1. Okay, let me call this as equation 2. Okay, so from here I can write, first of all, you are having this del A by L1. I will write this as del A by L1 plus 1 by L1 into ZA. First we have this ZA. Now we have ZA. So in place of second moment area theorem, that is in place of with this expression, we can write this as, this is equal to A1 x1 bar. Why A1 x1 bar? It is A1 x1 bar because you are having two moment area diagrams. You are having this moment area diagram, this moment area. So the actual moment area diagram will be the resultant of these two diagrams. So if we have to use this expression, ax bar divided by ai, we have to make use of both these moment diagrams, the free moment area diagram and the fixed moment area diagram. Okay, so they are individual diagrams. They do not exactly represent the moment. Their resultant represents the moment. So this expression is to be used for both. Okay, so it is a1 x1 bar divided by ei. I will take this ei out because this will be the common for all. Okay, well, this is ei. I will take it out. Plus, so we have used ax bar for this. Now we are having this diagram. Okay, this diagram we have divided into two right angle triangles. One is having green side and that is having yellow side. First, let's talk about this green side. Okay, the green side moment will be equal, green side area will be equal to ma multiplied by L1. So it is ma into L1 divided by 2. ma into L1 divided by 2. And how much is the centroid? It is L1 by 3. So into L1 by 3. And you are having one more right angle triangle here. Its area is equal to MB into L1. So you have plus MB into L1 divided by 2. This is area multiplied by the centroid, multiplied by distance of the centroid. You have to take the distance of centroid from here. Why? Because while we were doing the second moment area theorem, we were taking the centroid or the first moment with respect to the axis where you were calculating the tangential deviation. So that is 2L1 by 3. So multiplied by 2 times L1 by 3 is equal to, you have delta C by L2 plus, then we have 1 by L2, and you will also be having EI there. I will tell you why. Multiplied by, so first expression is A2 and X2. Because why you are taking here X2? Because here the tangential deviation is ZC. So you have to take all the centroidal distances from ZC. So it will be A2 X2 bar. Okay, plus the area of this right angle triangle first, that is MB into L2 divided by 2. And how far is it centroid from here? Its centroid is 2L2 by 3. that is 2 times L2 by 3 plus the area of this right angle triangle, that is having MC as one of the side. It will be MC L2 divided by 2 multiplied by L2 by 3. That is how far its centroid is. Okay. So what we will be doing, okay. Now look at the z-intercepts. Okay. The z-intercept on the left-hand side is positive, while as the z-intercept on the right-hand side is negative. This is a sign convention. Okay. You can take it otherwise. So what you can do, you can take this z-intercept as negative. This is negative. This is on the lower side. And this z-intercept on the right-hand side is, this z-intercept on the right-hand side is positive. Okay. So what we can say, we can easily say that when you are talking about these z-intercepts on the left-hand side, these are all negative. So instead of positive here, you have to write negative. Okay. That's why, because z on the left-hand side is negative. That's okay. We are done with this. So what we can do, let's multiply all the terms. Therefore, we will get MA, or I can also do one thing. Let me use a sign convention in which we can say, using sign conventions, you are free to use. You can at least say the moment the z-intercepts on this side are positive, the z-intercepts on this side are negative. Since most of the books have done it like this, so as not to create confusion among students, let's take the same conventions. Otherwise, we are free enough to take the conventions. Our results will not change. Okay. Therefore, taking these conventions, what we can write, MA into L1 by I1. I1 is the moment on the left side. I1. Okay. And I2 is the moment on the right hand side. Let's believe that their Young's moduli are same. You can also change them. It doesn't matter. Plus 2 times MB into L1 by I1 plus L2 by I2 plus MC into L2 by I2. Okay. Becomes equal to minus 6 times. Once you perform these multiplications, it becomes minus 6 times A1 X1 bar divided by I1 L1 plus A2 X2 bar divided by I2 L2 plus 6E times, or I will write the 6E term downwards, plus 6E times multiplied by delta C by L2 plus, minus delta A by L1. Fine. Sometimes what we have, we will usually be having the beam in which moment on left hand side, second moment on left hand side will be equal to second moment on right hand side, that's equal I. Okay. And we do have sometimes the conditions where delta A is equal, delta C is equal to 0. Okay. So in that case, the overall Clapeyron's 3-moment equation will be, in that case, the overall Clapeyron's 3-moment equation will become, let me clean the surface over here. The overall Clapeyron's 3-moment equation will be, the Clapeyron's 3-moment equation in that case will become MA L1 plus 2 times MB into L1 plus L2 plus MC L2 is equal minus 6 times A1 X1 bar divided by L1 and minus 6 times A2 X2 bar divided by L2. And this is called the Clayperons 3-moment equation. This is called Clayperons 3-moment equation. Okay, this equation we'll be using for drawing the shear force and bending moment diagrams of the continuous beams. Now the question is how to make use of this equation for finding the shear force and bending moment diagram of the continuous beams. That we shall be discussing hopefully in the next class. In the next class, we'll be talking about the applications of this equation in finding these reactions and in drawing the shear force and the bending moment diagrams. That's all for today. Thank you very much.